today we're going to be looking at aggregate data. We'll be looking at lists. We're going to be looking at trees. Our representation of trees is basically going to be lists of lists. So that'll be the second thing that we'll do in class today. And we're going to be looking at is lots of different procedures on how we can manipulate lists and do various things to lists. So on today's handout is all the code that we'll be using for today. The first procedure I'd like to write is called length. And it takes in a list. Be careful when you're writing your variable list that you don't write list, L-I-S-T. Or you're going to have problems. So I'm going to do L-S-T or L or whatever. And that's not a 1, it's an L. Okay, so let's actually recall the box and pointer diagrams before we start writing it. Let's say that we define a list. And we'll define A to be a list of 1, 2, 3, 4, 5. What does the box and pointer diagram look like? Well, it's a list of 5 elements. First, second, third, fourth, fifth. And then A would be bound to this. When we say list, let's say we say list 1, that's equivalent to saying cons 1 nil. Similarly, list 1, 2 is equivalent to saying cons 1 to the cons of 2 and nil. It's just like a shorthand for writing lots and lots of cons statements. So if we see here, list 1, well, we're consing 1 to the cons of 2 to the cons of 3 with the cons of 4 with the cons of 5 nil. Yeah.
We see this picture without seeing the list above. How would we interpret A? First arrow into the first box.
Well, so, okay, so let's say, let me draw some other list structure. Okay, so we don't see anything above it. So what is B? So B is bound to this thing. So if I ask scheme, I say B and evaluate, what will print? It's going to print the list 2, 4, 6. So when we look at this, normally lists are drawn in this straight line across. It makes it a lot easier for us to see it. We could just as easily do something like this. That's hard to read. It's just harder to read. So generally we draw a list straight across like this, which is a good indication to you that it might be a list. And what really gives us the idea that it's a list is that last cell, that we've got a nil in the last cons cell.
But we would read that as B is defined as that list.
Right, B is bound to the list 2, 4, 6. Okay. So just a little bit of review of yesterday. How would I get the number 4 returned from scheme? Right, so we're going to take the car of the cdr of B, which we could also write as catter B. Okay, and if I wanted to pull out the 6, cadadr. No, it's not. No, it's cadadr. Sorry, there's no extra A in there. So it'd be the car of the cdr of the cdr of B.
What would happen if we did just the cdr of the cdr?
What would we get back if we asked for the cdr of the cdr of B? Well, if we take the cdr of B, it's this, right? We take the cdr of that, we're going to get the list 6 returned to us. Okay.
Does it give you anything for nil, or is nil really nothing?
No, actually, what nil is bound to is false. So if we ended up asking for the, let's see, that would be if we wanted the nil, it's the cdr of the cdr of the cdr.
Wouldn't it be the car of the cdr of the cdr?
No, you don't need the car, it's the cdr cell. So we take the cdr, the cdr, the cdr.
Okay.
But wasn't two cutters?
Return a con structure, like a 6 dot fault.
2 cdrs would return. No. Okay. So if you've got a con cell that looks like this with anything in it. Okay. Now, we talked about conses yesterday. Let's say we said cons 1 to 2, that this would print out 1.2. It would look like this. 1, 2. Now, if we had a list of one element, would say cons 1 nil, it would look like this. Okay. Now, you could say, well, wouldn't it print out 1 dot paren, well, not paren, 1 dot nil? And it doesn't do that. Just like we saw yesterday that the dot open paren went away, a dot nil also. Scheme just eliminates that when it's printing it back at us.
What would we get if we did the car of the cdr, the one that was just the car of nil, essentially? Would that give us an error? Or?
What happens if we ask for the car of nil? Is it a box and point? Is it a box and pointer structure anymore? Just the nil. So it is going to be an error. So when we're writing procedures to cdr down the list, that's what we're going to call it. We'll be doing today. We'll be cdring down the list. We'll be doing something to the first element and recursively calling to do the rest of the elements. It's called cdring down the list. We need to make sure we check to make sure our list isn't nil. So we need to base case on that. We need to get out of those. Yes?
Is nil used just in this context, or is it a more general logical empty set?
Nil can be used as, I think we've seen it used before as a return value. If there's no answer, we just return nil. So it can be used that way. It's most often used in lists, but you can use it. It basically maps to false, so you could use it as a logical value if you wanted to. But if you're using it logically, it would make more sense to write false rather than nil. But you can use nil. That's fine. They're the same. Yeah, nil is false. Nil is defined false, yeah. Okay. Any more questions on just sort of box and pointers, cars, cdrs, conses?
You are explicitly saying that you can just put a bunch of D's in and use that as a command in list, right? You're not just making shorthand, right?
No, this is actually a command for scheme. The maximum number that you can put between the C and the R is 6. So if you need to go to 8, you would need to break it down to 6 and 2 or 4 and 4 or something like that. So it can go up to 6. And it is a shorthand that is supported in scheme. It's not just me writing on the board. Typically, I don't shorthand commands on the board. I want to show you guys what you can go and type in.
Can you put nil in the car box of a pair, and will that be an element in your list then, or will that end the list?
Can you put nil in the car box? Sure. It's sort of like when we wrote the infinite loop. It's sort of degenerate. It's a little bit weird, but we could do that, sure.
That would be done by consing the nil onto.
Yep.
If you had a list that pointed to a list, and the list it pointed to is nil, is that a representation you get?
Okay, let me write that down. Okay, so the question was, could you repeat the question? The list was if we had
A list of like 2 elements, and and the first element points to a list.
So we had a list of 1, 2, 3.
Right, except, so what would the box and pointer be if list 1, 2 was actually empty?
How can list 1, 2 be empty? List 1, 2.
Empty list.
Okay, then it wouldn't be list 1, 2. It would be the empty list. Nil. Or,
So what would
okay.
what would the box and pointer
Okay.
be?
So we'd have a list of 2 elements. And this one, actually, it might be easier to look at it like this rather than crossing through that first one, because it really makes more sense to cross through it when it's the last element. And we could do something like that. We might end up doing something like that if we're consing some logic value. So we're checking to see if A is greater than B and consing that onto a number at the end. And then we could end up getting nil or actually false. Yes?
Why doesn't it look like the structure for cons 1, 2 over here, where you just have nil in the first box or slash in the first cell? And
the reason it doesn't look like that is because we're using list rather than cons. Okay, so list has an extra cons at the end, and it cons is that nil on in the very last one. So it expands out to the cons of the cons of the cons of the cons, finally nil. So that's what list expands out to. Other questions? Let's look at an example of writing something to manipulate a list. I mentioned we'll be cootering down the list. So just breaking up the problem where we operate on the car and then we call on the cooter. Okay, so we're going to define the length of the list. So the first thing that we should do is we should check what? If our list is empty. So the way we say that is if null question mark. I believe that John told you about the convention in the scheme that if there's a predicate procedure, it has a question mark at the end of it. So we're saying if null, and what that does is test to see if our thing is equivalent to a nil. If our list is null, what's the length of our list? 0. Otherwise, what should we do? Right? Right. So if we don't have an empty list, let's actually look at it over here. Let's look at it on a non-degenerate list. So B is 2, 4, 6. So what happens? Let's say that we call length on B. Okay, so which means that we're calling our procedure on the list 2, 4, 6. So is our list null? No. So we're going to return 1 plus the length of the cooter of the list, which is the list 4, 6, right? I'll be a little pedantic right now. And actually, when we're writing this, so we don't confuse this with us trying to apply 4, 2, 6, you can write this with this quote. We'll see what the quote means when we start talking about symbols and quoting. But if you wanted to shorthand list 1, 2, 3, we could write quote 1, 2, 3.
Are those exactly the same, or is there some subtle difference that we will learn in the next little bit?
No, Scheme will evaluate this to be a list of 1, 2, and 3. There's no. But yes, sorry.
What happens if you put too many parentheses at the end?
Then we're going to get some sort of an error. Well, actually,
Take off one parenthesis from the top.
take off one parenthesis
No,
from
no,
it.
no, no.
Here?
Yeah.
Did I have too many?
I think so.
No. Cooter length plus if define. Dunk, 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 dunk. I'm almost as good as Edwin. I do make mistakes. I'm pretty good about the parentheses. I have a little parentheses stack in my head. I remember how many I have. In any case. Yes, I am a nerd. What can I say? Okay, this is, what's the length of 4, 6? Is our list null?
Nope.
No, it is not. So we're going to add 1 to length called with the cdr of the list 4, 6, which is, right. Okay, so now we have plus 1, plus 1. This is not null yet. Plus 1 called on the cdr of 6, which is now nil or the empty list. So we could denote this as nil or the empty list.
Like the length of that.
Rather, yes, the length. Sorry about that. I was so into showing you the different things that I forgot the first part. Okay, so now we call length on the list. It is now null. So we have 1 plus 1 plus 1 plus 1, 2, 0, which will collapse up to 3. What type of process have I generated?
Recursive.
It is a recursive process. How could I write this iteratively?
Helper function. Counter.
Yep. We would add in a helper function with some sort of state variable for a counter. So we could define length of list, define iter list, and then the count.
Do we need the list and the iter?
Do we need the list? In effect, it's sort of our counter, right? Because this is going to be the count that we're returning.
Okay.
And this is going to be the list as it is on our recursive call. We're walking down the list. So we're sending in,
Recur on the program length, we want to recur on iter. Okay.
right, because if we forget, right, if we call length, then we lose our state variable for counts. So we do need to be passing that in our internal state. Still going to look pretty much the same. I'm going to check to see if our list is null. Now here's a little bit of a difference. What do we return if we have a list that's null? Count. We return our answer. Otherwise, what are we going to do?
Iter of the list and 1 greater than count.
We're going to iter on the cdr of the list, and we could write increment count. Or we could say plus 1 count. I just use increment. Okay. Oh, yes, we need to call it. I'm sorry. Got a little over rambunctious on my paren matching there. Now we would call it 0. Yeah, this is going to do the exact same thing, but with an iterative process. So if we had a list of 500 elements, we're not delaying 500 operations. So if you're going to be dealing with really long lists, as you guys saw in problem set 2, we do have a maximum stack depth. We have a max amount of stuff that we can remember. So if you guys are dealing with lists that might be tens of thousands of elements long, which strategy would be better to go with? The iterative strategy. Right. Okay, questions on length? So basically, sorry.
Sorry, the null function, is that a scheme thing?
Yep, that's a scheme primitive. Null question mark is a scheme primitive. We also have kind of a, we also have one pair and number. Can I explain these before I answer a question? Sorry. So pair is going to return true if we have any sort of list structure, whether it be a single const cell or it's a full list. It's just looking to see if there's something. It's looking to see if there's a const cell. That's a
Can you
pair.
give an example of what would return false for pair?
Okay. And number is going to return true if it's a number, and false otherwise.
Can null question mark be used for any variable to see whether it's defined or not, or just list in terms of list structure?
Well, if a variable is unbound, right? If it hasn't been defined, then there's nothing there. It's going to give you that error even before you can get to checking that it's null, because scheme is going to say, what's the value of this? Because remember, to evaluate this compound expression, we're going to evaluate the sub-expressions. When it goes to evaluate the unbound variable, it's going to spit an error out at you. So it's not even going to get to applying null question mark to that, because it just can't, because it has to check the sub-expressions, and that's where the error is going to come out.
So are the lists we have before that we were looking at, which they had a nil in that car box, this length would count just up to that point, right?
No.
No.
Because our list wouldn't be null. Our list is null only if it's actually a nil or this. But it's such a degenerate thing to do with a list. But we would have so weird. But we would have had a nil first, so we would have actually counted that as one of our elements.
So you say it only null only returns true if the list.
No, only if there's a nil. Null is true only if we do that.
Right, but
if we had anything box and pointerish.
So if the nil was followed by anything, it would return.
I'm really troubled by this nil followed by stuff. This is really not something. It's just wrong. It's just you could see. I don't see a case where I would put a nil in.
I guess the more important thing is just that I'm wrong, right?
I wouldn't call it the more important thing, but null is looking for just the empty list, and you'll see in the book they'll write the empty list.
How can you call it an empty list? Because that I mean, it's not an empty list. It's not even an empty cons, right? The first cell of the cons has a number in it. It's an empty cell in a cons, right? It's not a. I mean, if I'm not understanding how. That's an empty list.
I wish John were here, because I bet John could come up with an alternate explanation that I'm coming up with that would hopefully make it clear. Get up and go.
Well, I mean, the only thing would be, as in, it's sort of along with the homework, but if you have a list with no cards in it.
If you have a list with no cards in it, it would be the empty list.
Right, and that's an element off your list of card information.
Right. So basically, yes. But actually, when we start off, so the homework is asking you at the end to change your representation of a hand to a list of 3 elements, with the first one being, is it the total of the up card? The up card. The second one pointing to the total, and the next one pointing to the list of cards. Remember, when we create the structure right away, we have at least one card. Right. So we're not pointing at an empty list there.
I know I have done things where you've had a list that has contained empty lists. I mean, it's probably just an exercise.
Yeah.
And another way to think of the null list is there's also a predicate empty. And that
it was not. I kept getting.
Yeah.
Is there? So yeah, I think that the book may talk about empty list question mark, and it's an abstraction, I believe. So like I was saying, the empty list is an abstraction in the book for nil. They do some abstraction on building up lists for that. I'm not using any abstractions. After I spend a lecture telling you about how good extraction is, today I don't use it. How about that?
One slash is called an empty list. One single cell with a slash in is an empty list, whereas the empty list, the set of 2 boxes, the second of which.
This is not an empty list because there's got to be something in that first cell, right? So this is a list of 1 element.
Okay, right. So you said null looks for the empty list, so somewhere in that there is.
So the empty, so here the empty list is defined as nil. The empty list is nil by definition.
Just a single nil.
Nil. That's the empty list. By definition, nil is the empty list.
Okay. Great.
Okay. And by number, you mean any real number? Or just integers?
I actually don't know the exact specifications. I may have R4 with them. Probably not. I'd have to look that up. I don't know the exact specification of number.
I think you just said it before, but I missed it. If there was a nil in one of those boxes, and you call it with null question mark, you'll get true or false.
It's only, so if my list were something like this, if I call null on this, that will be false. Because all it's looking for, the car of this, it would be true. Or the cooter of the cooter, it would be true. But this is a list structure and it is not null. Okay? Yes?
So when you were iterating through that 3-element thing, and you were looking for null on whatever
The null list.
right, that basically what you're doing is the cooter of the particular con is a nil, so it's saying there is an empty list following that basically, and that's why it's null.
Okay, let's look at cootering down the structure here. If we've got the list B, okay, we call length on it. So the first thing we say is this null? And it's not, it's a list, all right? So what we're going to do is we're going to add 1 to calling length on the cooter, which is this, okay? So now we call length on this, is that null? No.
So, right, but I guess what I'm saying is the cooter is that which is pointed to by the second element in the
Right.
class, right? So on your last element,
When we finally call it, we return this. There's no pointing to. That will actually just return a nil. So when we finally call it last cooter, and then it'll say null, and that'll be true. So yeah, when we take the cooter, we take what it points to. And in this case, it will return the nil, because it's not pointing to anything.
so it's not actually, the cooter actually isn't that cell of that last con, it's what that last cell is pointing to.
It is pointing to something, right? So we've been denoting nil that way. You could just as easily say nil. It's a convenient notation for us when you're looking at it. Once you get used to box and pointer diagrams, you'll be able to look at this and say, oh, it's a list. Whereas if we dropped down like this and said nil, you'd have to think about, oh yeah, there's the nil at the end. It's just more convenient to see that slash mark in the last cell. Okay? Should we write some more procedures for cootering down lists?
Holly? I just had a question about the number function. I assume that returns true for any kind of number. So
That's what Sam asked me, and that's why I was asking if anybody had the revised report. I don't know the exact definition of that. I would need to look that one up. Okay. I think it would be if it were any number, but I really don't want to tell you that if I'm not sure.
Yeah, I was kind of curious because of our exercise yesterday where we were coming up with radicals, where we would want to, if we were doing some sort of function where we wanted that make radical thing to only sort of work for what we consider to be regular radicals, we want to check and make sure it's a whole number that we're putting in. I was just wondering if there's an easy function to do that, or if you have.
Rob will tell us shortly. I'll erase the board while he's looking.
Another question, what if we apply that to a variable name that's bound to a number?
Well, okay, so what if we do apply number to A where we've defined A to be 2? How do we evaluate that compound expression? Well, what we're going to okay, where we're going to count 1, 2, 3, 4, 5. The book actually says that there's a convention for counting 0 as the first element of the list. Well, we keep talking about it as the first element of the list, and I think it's going to start getting confusing. So let's just say first element is the first element. These aren't arrays in C. So we don't really need to start counting them at 0. So if we're going to count to get the nth element, how can we do this? Well, we're cootering down a list. So the first thing we probably want to check is to make sure we don't have a null list. Actually, I believe we're going to need to use a cons, yeah. We could do an iterative. I've written everything recursively in my code. I'll leave it as an exercise to the reader to flip it all over to iterative processes because it would be fairly straightforward. Okay, so if our list is null, what do we want to return? No. We have no nth element. Okay. I put in a special case in the code to check to see if n was equal to 0. because the book defines it one way, we're defining it another way, I'm just going to spit out that that is not defined in our procedure. You can't get the 0th element.
How much should you use that? Less than or equal to 0, right?
Sure, you could do that too. Less than or equal to n0.
More quotes or shortening your
No, actually, so this is a string, and it returns the value of the string, which is just the string itself. We haven't talked about strings yet, but this will just return value and then the string not defined. Because if we use the error procedure, and if any of you guys, have you guys tried using error? You say error and then some string, it pops you into the debugger. So I don't really want to pop my user into the debugger. I just want to tell them it's not defined.
And the difference between display?
What's the difference between those two?
The difference between display and this is I believe this does not strip out the quotes, and it will print value before it. Right, so if we want, basically, this is being returned as the last value. Let's say we wanted to do some other statements after it. Then we would need to use display to force it to print out. Here we're just using the trick that the last thing is going to be the value returned. So we make a string, the string is returned. We could do display. We could say display not defined.
But what's the difference between the last sentence you wrote and the previous one? If the list is null, isn't n equal 0?
No, not necessarily. So I could call, so n is asking for, let's say I had nth on the list 1, 2, 3, 4, 0. I could make that call. Now if I make that call, I want my procedure to say that's not defined. I don't know what the 0th element is. So if we were cootering down the list, I know what you're asking. So you're basically saying if we were making recursive calls, and we're asking at the end maybe null, at null our n might have been gotten down to 0. But we're checking the null list first, and then we're checking, this is really more error checking on the user's input. Okay, so the next thing we check to see is if n is equal to 1. If n is equal to 1, what do we want to return? Car of the list. Otherwise, we will do what? We'll call nth on the cooter of the list, and then decrement x. Sorry. And x, a, b, you know. That's what the interpreter's for, being you did it wrong.
Have both nth and n.
Well, nth is just the name here, right? So it's nth is my name. And then I used n, just to be clear, if I'm asking for the nth element, I'm probably pulling in the n. So that's not a problem. It's not going to have a problem with that. Yes?
It seems to me that if we were writing a higher function that called on nth, it was expecting nth to return a numeric value for some reason, that was then being evaluated in that higher function as a numeric value, and then for whatever reason we wound up with n equals 0, we'd be returning a string into another function that was looking for a numeric value, and we would then get an error that was saying that we were trying to pass a string into maybe sort of a numeric operation. It seems to me that would be a lot harder to debug than if we just went ahead and went into an actual error message in this lower function. I'm just kind of asking the questions about coding practices.
Well, I guess there are two theories. The one is that you just say nth is defined as taking a number 1 or greater, and it will return the nth element of the list. And if the user calls it incorrectly, all bets are off as to what happens to them. So if you say, this is what my procedure does, and you call it the wrong way, I'm not going to guarantee it's going to do anything nice. So we could look at it that way. We could generate an error message. I think it seems nicer to the user. Let's say you had some naive user of Scheme who was using nth, and all of a sudden you're popping them into the debugger, and they didn't write the code, and why are they getting into the debugger? So that's one reason why you might not want to do it.
I guess I'm just wondering if there's any sort of legitimate reason why you would have n equals 0. That, that wasn't the result of a programmer using your nth function incorrectly. I mean, there's obviously the extreme cosmic ray example that John gave.
Yeah, okay.
Yeah, so basically, I mean, I didn't even need to have that check for 0 in there.
Right.
Well, but if you passed 5 into that, you would go all the way down the list to the very last element. And then
You'd
start
get
looking-
nil, and you'd pop here. You'd eventually could have down the list. So in fact, we don't really need to have this check. I was just putting that in there because the book had said, we define nth as starting at 0. I prefer to start it starting at 1, so that's why I put the check in there. We don't even need to provide that check. Because eventually, you're going to get to the end of the list. Okay? We don't have infinite lists, although we'll see in a few weeks that we have streams, which sort of simulate infinite lists, but in any case. We don't have infinite lists, so eventually we're going to hit the end of the list. So that'll get us out of this recursive procedure. We won't end up being in an infinite loop. So we don't really need to check for the 0. So we can take that out. More procedures? More procedures. More is good. Let's return the last element. Okay, so cons. First thing we check, is our list null? If it is, no.
Now we can do a null on the cdr of list.
Right. So now we say null cdr of the list. What we're looking for in this case is something like this. We're looking for the end of our list. So we're looking to see if the cdr is nil. If it is, what do we want to return? The car of the list. Otherwise, last on what of the list? Cdr of the list. So this will return the last element of our list.
You could also combine length and nth sequence. You do the same. Take the length of the nth of the length.
So an alternative method for defining last was suggested, and it is define last list to be the nth element of the list on the length of the list. So that's an alternative way to write last.
That's not very efficient, right? You have that twice.
Well, we're going to cdr down the list once here, and then we're going to cdr down it again here. Okay, so it's a little less efficient. We're cdring down the list twice. Small list, does it matter? Not really. Is it going to matter if we have a list of 1,000 or 2,000 elements? It'll start to become noticeable. Yep.
I'm still have just a little bit of confusion about null.
Sure.
Just as far as what it takes as an argument, because it seems like
Null can take a number, a pair. Yeah, it's just checking to see if it is null or not.
So, but a list like here on the we do both examples here. Cdr list is actually returning just an element, right? It's returning a.
Well, cdr list could return a couple of things. If we had this as our list, the cdr of our list would actually be that.
Okay. So when it's checking for a single element, which like in this case it was,
right.
Then it checks whether that element.
So cdr, right.
And
so basically, what null is defined as is looking to see if what you passed it is the same as nil. And if it is, it'll return true, and otherwise it spits out false. That's what null is doing. It says, is what you gave me equivalent to nil? Yep, great, true. Otherwise, I don't even care what it is, I'm just going to say false. It's not nil. So we could pass it anything. But we're looking for the cases when it is nil.
And the cases when there would never be the case that a bunch of cells would evaluate to null, right?
No.
Even
No, a list isn't going to return to, the only time we're going to get nil is if we have nil. In that case, it's what's pointed to by that cdr cell on the list.
Care what the argument itself can be a list or
It could be anything, right? As long as it doesn't evaluate to nil, it's going to return false. And I actually think you could pass it a procedure, I would think, too, because that's not going to be nil, therefore it is false. Sorry. Right, we don't type scheme, remember. There are no data types. Okay. Let's write a procedure to scale every element in a list by a factor. So we could write define scale list. A list and some factor n. Check that it's not nil. And if it is, what? Return nil. Okay, this is a little different from our length procedure, our nth procedure, our last procedure. Here, we want to return a list. So rather than adding a number or returning a number, we need to build up a new list structure. So we're going to cons two things together. What's the first thing that we'll cons? The scaled car. And we'll cons that to the cdr, or actually the scale of the cdr, of the list, and n. So remember, list of some number of elements is equivalent to cons 1, cons 2, cons 3, nil. So our base case is going to do the right thing. When our list is empty, this returns as a nil, and we start consing up, and we've got a nil at the end, so we're rebuilding our list. So we end up with a string of delayed operators, cons, scaled value to cons, the next scaled value, cons, value, nil, which will build up our list for us.
Probably would need to do a number check to make sure that the list wasn't A, B, C, D, E.
We don't tend to do lots of error checking in Scheme.
Okay.
We just don't tend to do that. We're just assuming smart users, which you guys all are. So yeah, we don't tend to do error checking in Scheme. We're just sort of assuming, you know, look, we got scale list, and it's defined as taking in a list and scaling each one by a factor of n. And if you're kind of dumb and pass me a, you know, some sort of symbols, you know, or strings, all bets are off. I'm going to error out on that one.
It can make this language very difficult to debug about.
Sure. There's no typing in the language, and because there's no data typing, the compiler or the interpreter isn't spitting out problems for us until things start to run. Yep. So it might be harder to debug, but that's generally
That's the user's problem, not yours.
Well, no, one would assume you're going to deliver working code to the user. But see, the thing is, the user has to be smart. You have to say, you know, this is going to take a list of numbers. And if you don't give it a list of numbers, then, you know, C would be pissed off at you too if you did something like that, or Pascal.
It would, because it's a compiler. I mean, it could tell you more to say, hey, look here, something's wrong. This, you might have to run through 3 minutes of code to get to the point where it finally failed.
No. Well, because you could run the code, but when it pops into the debugger at the failure point, it's going to pop right to the failure point. Just like the compiler in C would point you to the error that came out. And in fact, one could argue that the C compiler is not so nice either, because sometimes if you forget a mark somewhere, it might pop you several lines of code later or ahead of where the error actually is anyway. C isn't perfect.
Saying that with the input, it would check the input to see if the input was right, and then it would immediately stop you there, as opposed to running through the program.
Sure, but when it did fail, it would point you to exactly the point at which it failed if you entered the debugger. Because remember, the debugger is just going to show you the execution stack of the program, and the top will be where it had the problem. So we can look through that to see where the problem was. It's really more of a religious issue.
So just this thing of changing a list. The only way you can change a list is build a whole new list. Is that correct?
Yes, for now. So the question is the only way we can change a list is to build up a whole new list? And I'm going to say yes for now. Because there is a way to go in and modify lists and mutate them and do all sorts of fun stuff like that. But we're not going to do that now. Let's learn about lists. Let's use them this way. And then we'll learn about mutation in a little bit.
So to do that iteratively, you need a new list?
Yeah, things like this start getting a little more difficult when you're doing them iteratively. Because you need to use something called append. Because if we were calling this iteratively, and we had our new list as part of this, so basically we would have a list 1, and then somehow we'd, well, say 10, we had 1 times 10, and then we'd want to add the element 20 in. So if we can't cons, if we cons 10 to 20, that gives us this. If we say list of list 10 and 20, that gives us this. Okay. So what we would need to use is something called append, which we may write. Append takes 2 lists, list 1 and list 2. And it returns the first appended to the second. So if list 1 were the list 1, 2, 3, and list 2 were 4, 5, 6, it would return 1, 2, 3, 4, 5, 6. So that's what append will do. So when we're writing append, what we're going to do is we're not going to cutter down both of the lists. We're only going to cutter down the first list. So what I'm going to say is if list 1 is null, what should I return? List 2. So what I'm going to do is I'm going to cons the first element of list 1 to the cons the second, cons the third, cons this, and finally we'll 1, 2, here the car, the cutter, da, da, da. Do we need a recursive call here maybe? Yeah. Append. I'm going to append the cutter of list 1 to list 2. 1, 2, 3, 4. So let's look at this.
But if you rewrote scale lists using this, it's just recursive anyway. If you try to rewrite scale lists iteratively, but you call it a recursive append.
Right. Well, right. Then you're still going to generate a recursive process. Append is
append the list over and over and over and over again, as opposed to just
building it up once. Right. Huh?
Very big code.
It could be, yeah. So now's actually when when we're operating on numbers. I mean, barring Towers of Hanoi, we haven't seen any really cases where the space. We haven't operated on numbers large enough to really see the orders of growth come into play. But with lists, we're going to start seeing how things can get really big really fast with lists. Same thing works with numbers. We just didn't see any examples where the numbers got really big. Same thing is true of that, though.
Is that list 2 at the end there? Or that last append?
Yes, it would be list 2 here.
Do we have an order and scheme to reverse list?
Do we have an order to reverse a list? We could write one to reverse a list.
There are a lot of these that are...
Some of these are primitives, but not all of them.
I actually think reverse is one of them.
Reverse probably is, because it's one thing that you'd want to do. How would we reverse a list? Well, one way we could do is we just use last. We wrote last, right? We wrote to get the last element of the list. So we could say, if, it's not beautiful, but we could do it that way. So we could say if the list is null, otherwise return nil. Otherwise, cons the last element of our list to the recursive call on reverse of the cdr of the list.
Keep getting the last element.
Oh, yes. Sorry. Yes. Okay. This is why you prepare for lecture. I didn't prepare reverse. Let's try writing reverse again. Yeah, but cutting off that last element's going to be hard. Yeah. Okay, so let's actually do an iter. We're going to have list 1. Actually, we'll just call it list. On the list with our new list. Okay, so now if the list is null, we'll return nil. Otherwise, oh yes, sorry.
Onto the car of list onto new. Well, you could just and then recall with new being.
So okay, so let's say we call iter at this point. So we'll call iter on. Let's see, the first thing, we're going to take the cdr of the list. And then let's say that we cons the car of the list to new. 2, 3, 4. What would be our call? Yeah. And that nil gets us that first nil at the end, when we first start out, the bottom one. Oh, yes. There you go. That's reverse. Why were we reversing a list? Was there something we were driving at with reversing the list? Oh, we were just reversing the list. Okay. I didn't know if there was another example that we were using reverse for. Okay. Reverse is a good thing. I like it.
Is last the primitive?
I got to admit, I don't know what all the ones I would have to look at the report, where I'd have to type it in and evaluate and see if it's there. I just redefined everything in my buffer. Okay, so there's reverse. Now, are you guys feeling comfortable with lists? Could I move on to trees? There are a lot more list procedures written on the handout. Okay, I'll leave it for you guys to look at that. If you have questions on it, certainly feel free to ask me, ask John in recitation. We can go over more of those procedures if you guys have questions on it. But I would like to talk a little bit about trees today. Now, trees are just going to be lists of lists. So we could define a tree. Let's see, I defined, let's look at tree 2. So define tree 2 as the list of list 1, 2, list 3, list 4, 5, 6, list 7, 8. Notice the way I have written out my code. This allows me to see that this list is of 3 elements. And this one, 2. I didn't write these out that way because when it's single numbers, it's not so hard to see that. So our first list, let's draw the box and pointer diagrams. Our top list is a list of 3 elements, where the first element of the list is a list of 2 elements, with the first element being the number 1 and the second being 2. Our second element is a list of 2 elements also, where the first element is the number 3 and the second element is a list 4, 5, 6, a list of 3 elements.
Should there be another in parentheses?
Okay, one more list. Third element is a list of 2 elements. 7, 8. And that is bound to be tree 2. So, here's another way to think about it. Here's our top node. The left-hand side of the cons will be our left branch. Well, it's a list, and the leaves are 1, 2. Okay. Then we have, this is not a binary tree, it's just a tree. The second one is a list of, the first branch is a list of, there's just 3 rather. And the right branch is going to point to a list of 3 elements. 4, 5, 6. And the third branch over here is the tree. 7, 8. Okay. So this is the box pointer diagram for it. This is another way to represent it if you wanted to just draw the tree out. So let's write a procedure to count the leaves of a tree. So if I did have this tree over here, what would count leaves return? How many leaves are there? 8, conveniently, because I numbered them 1 through 8. Okay, so we've got 8 leaves. The way that we compute count leaves is the first thing we're going to check. We're still operating on lists, so we still want to check to see if we've got a null tree. So if our tree is null, is nil, is it a leaf?
0.
No, it's a 0. Okay, now we could say if it's not a pair, if it's not a pair, it means it's a single element, which means we've hit a leaf, right? We've hit a leaf. So we're going to return 1. If we don't have a pair, it must be a leaf. Otherwise, we will add the result of counting the leaves of the car of the tree to the result of counting the leaves of the cutter. Unlike our list where we knew each element was a single element, here the car may be a subtree, and so may be the cutter. So we need to call it both on the car and the cutter. So we'll count leaves on the car of the tree. 1, 2, 3. No, 1, 2. And then count the leaves on the cutter. Okay, now, I told you guys this wasn't a binary tree. It's not, right? Not a binary tree. But why, here, do I only have 2 cases? Why am I only calling on the car or the cutter? It's not a binary tree.
Because it is kind of a binary tree, but it's pointing to things that are pairs, which are not counted.
Right. It kind of, sort of, right? I mean, it has a structure of a con cell, right? Where there's something in the first, something in the second. So we sort of break it out that way. But it's, in and of itself, it's not a representation of a binary tree because we have lists of more than 1 element. But we only need to call it on the car and the cutter. We need to break apart the con cell into its 2 parts. Yes?
What's the second? How does that work again? Pair, tree, not
not pair tree. So,
What's the logic there? False, true.
okay. So pair tree will return true if it has a pair. Okay, so if it's looking at something that has a const cell, it's going to return true.
Only one. Or
Any.
Okay.
Any. Okay, so we said pair takes any sort of structure. If there's a const cell there, it's going to return true. So we'll nod it to get false. So when we have a number, or if we had symbols or something like that in the tree, that's why we're saying not pair. Because this way we're not forcing it to be a number. We could have said number question mark. Yeah?
Isn't there an atom question mark?
Yeah, I believe, yes, there is an atom question mark. And we could have used atom question mark.
So you're saying if we get an atom, then that's...
That's a leaf, right? So if we don't have pair structure, if we pass something other than pair structure, we're either going to have passed a 1 or we're going to have passed a nil. But the nil is going to be caught here. Right? So if it's not pair structure, then it's going to be a leaf. Right? So we've already pulled out the nils here. Now we're pulling out the leaves, and now we're recursing.
Can you have a list of one element which consists of a list of two? List 1, 2, double parentheses on each side.
So,
No, get right. No. List of, list 1, 2.
Sure.
Is that not paired?
This would look like this. So it's a list of one element at its top level. The first element is a list of two elements, 1 and 2. So is this going to work for count leaves?
Is this going to work for not paired tree? The first level isn't paired.
Sure it is. This is a pair. A pair is a const cell. Pair.
Even though the second part is nil.
We're not asking if the coulter is nil. We're just saying, is it a pair? And it is a pair. And I, thinking pear, tree, partridge. Anyway, so sorry, a little early for that. Yes.
Does not evaluate to true when the thing it's evaluating is false? Is that how it works?
Not is inverting the logical value. So if we've got a false, it'll be true. If we've got a true, it'll be false. It's just inverting the value, the logical. Okay, so that's how we count the leaves.
So that would work in length, right? You can call a tree on a list or
So the question is, could we define our length for list, which we had defined before, in terms of count leaves? Could we do that?
Sure. I mean, sorry,
Sure.
Just use it.
Sure.
Just rename it. Count leaves.
Would we? Ooh, no. Yeah, I guess we could rename it. We could just, I was going to write this.
Count leaves, yeah, which is just like saying define.
Define length to be count leaves. Sure. I was going to write it from
That will work differently than our original length.
What do you mean? Would it return the right answer then?
No.
It'll
Because isn't a leaf a value in a tree?
Oh, because it's not looking for the car. No, it will.
Give you 3.
If you want length to give you, it depends what you want length to give you. If you want to count each absolute element, that'll work. But if you just want the number of elements in the...
If we're assuming a flat list, right. If we're assuming, so the assumption here is if we had a list 1, 2, 3, yes, it's going to work the same. But if we have list 1, list 2, 3, it will return different things. Why? What did our length do? It was counting only the elements of the top level list, right? So in this case, it would return 2, but count leaves would return 3.
Yeah, if it's a tree. If it's actually a tree, they return different values. But if it's actually a list, they would return the same.
Well,
Or what I.
Well, okay, basically a tree is a list, right? If you maybe you'd say a flat list, a list of only one across, then it would return the same, but it would have a different behavior otherwise.
You could use it to, you could apply to the list, all the lists that are branching out of the original list. So you count the top list, the number of elements in the top list, and then, isn't that the same?
So you want to write count leaves using length? Is that the question?
Use length. I thought that's what.
No, the question was, could we rewrite length to use count leaves, not the reverse? So could length of a list be defined as count leaves of a list? But if we have a list of 2 levels, length will return 2 different things. That second list looks like this. So that's what the second list looks like. And length is only going to count this. Whereas count leaves is going to count the entire structure, the leaves on the entire structure. So they'll return different values in certain cases. Which is usually a bad way to define a function. Define a function is going to be defined as one way in one case and another way in another case.
What if one of your pairs has 2 elements instead of nil for the coulter? Does that mess things up?
Yes, it would, but we're defining our tree to be every element is a sublist, right? It's either a sublist or it's going to be a leaf. So it would definitely mess it up. Well, no, it would. Well, let me reconsider that question. Let's think about if we called count leaves on this tree. Would that work? Sure, that's right. So look, we come in here on the tree. It's not null. It is not a pair. So we're going to call it on the car and the coulter. The car is 2, the coulter is 3. And then this will bounce it out to be 1. So it will base case out.
The not pair will bounce it out.
The not right, we're not looking at the null. It's the not pair that's going to win for us here.
Is the definition of a tree, can that include, can it include those technically nested conses as well as trees?
Sure, I don't recall exactly how they define the tree in the book, if it's lists of lists of lists, or if it's just any sort of console structure. I don't recall the exact definition that they're using in the book for the tree. Yes?
Curious about the atom function. Will that return true for anything and everything that's not a pair, or only for certain things that are pairs? For example, if we called it on another function, would that return true?
A function isn't a pair, therefore it probably should be an atom. Do you have it? We can do this later too. Yeah.
I'm just curious whether you know off the top of your head.
I should. I don't. I should. I'm fairly certain if it is not a pair, it will be an atom, meaning that a lambda expression would be an atom. That would be, I believe that would be the case.
Single F to this expression, right?
Right.
It's just one expression.
Right. Right. Okay. Should we write some more tree stuff? More tree stuff. Yay. So, what I would like to do is write a procedure called fringe. And what fringe is going to do, it's fairly similar to count leaves, except that instead of counting my leaves, what I want to do is I want to return a list that contains my leaves. So, define fringe tree. Okay, so if given the tree that I just erased, I believe it had 8 elements, I would want to return this. That's what I want returned. A list containing the values of all of my leaves. Right, so we could just sort of flatten our tree that way by returning the fringe. So how would we do this? Well, sort of the same, right? Before, this is a way that we found leaves, right? So we still want to check that it's a null, not null. We still want to check if it's a pair, or not a pair, rather. And then we'll have a recursive step. So some of the structure is going to be the same. So we're still going to say cond null tree. And in this case, instead of returning a 0, though, a nil. And we're going to say not pair tree. So if we don't have a pair, what do we have? We have one of a single leaf, so we could return. Do we want to return a cons, or do we want to return the element itself? Well, let's defer. Let's look at our else case, what we're going to do. Otherwise, what are we going to do? Well, we need to do something to two lists that we're going to be building up. The first list will be built up somehow using fringe on the car of the tree. And the second one is going to be built up on the fringe of the cooter. Okay, we got some holes. Okay, I hear we want to append these guys. Okay. Now, if we're using append as our operator, what needs to be here? What does append expect as arguments?
Lists.
Lists. So what do we need to have here? List tree. 1, 2. Why? Why do we have to do append?
Because you have trees on both sides.
Because we're going to have, well, the fringe is going to return a list, right? So we're going to have a list here and a list here. We're putting two lists together, which is why we need to append them. We can't simply cons them. If we cons them, then we're going to retain some of that nested list structure of the tree. So by doing append, we'll get rid of that. Cool?
If we were
kinda cool.
consing, we basically just remake the tree, right?
If we were consing, would we remake the tree?
Wouldn't we just come up with something that's exactly like the tree we just had?
Could we just return the tree in the second part of the con and choose con?
That's what so the tree's a list itself, so we're returning a list and a list.
Well, in this case, a tree is not a list. In this case, a tree is an element. It's a leaf, right? Right?
What we're doing is returning a tree into a long list.
Right. We're basically, well, we're taking the leaves and making a long list, right? So in fact, you could also call this flatten. So we're flattening out the list structure. We're just making it one top-level list. We're pulling off all the sub-pieces and making it one full list. So I heard the question, what if instead of append, we were to use, I don't think the yellow, well, I guess it does show up, cons, and then just say tree here instead.
Except what comes back from fringe could be a list.
No, we're not returning a list. Yeah.
Let's follow it through. Let's build ourselves somewhat of a less complicated tree.
This is the identity tree.
Okay, here's a list of 4 elements and a lot of gory structure. Okay, we call fringe on this. Whack. Is it null?
No.
No. Is it not a pair? No. No. Otherwise, we're going to cons. The fringe of thunk to thunk. Okay, denoting thunk and thunk. Well, you know, let's actually expose, draw it out. Oh, why, oh, why? Why, oh, why did I make this so large? 1, 2, 3. Okay, so we're consing the fringe of this thunk to the fringe of this thunk. Highly technical term. thunk. Okay, why don't we just look at the fringe of this? Okay, so is it null? Is it not a pair? Mm. It is a pair. It is a pair, right? It is a pair, therefore this is false. So we're going to cons the fringe of the car to, which is 4, to the fringe of nil. And what does that give us back? The list 4. Whoa, that's not good. That's not what we want to be doing, right? We're just rebuilding the list. We're rebuilding the whole tree structure back. So it's a beautiful little procedure that'll do pretty much nothing. It'll actually do something. So what it'll actually do is it'll build us a copy of the tree. We haven't talked about this yet. But when we create lists A and B and then we cons those two things together, it actually points to the structure A and B that already exists. So if we use this, it would actually make a brand new copy of our tree. But we'll talk about that later when we talk about symbols and things being EQ, EQV, equal, all sorts of other things like that.
I'm sorry, I blinked on that last.
Don't blink in this class. Okay, so we're consing the fringe called on the car, or 4, to the fringe called on the cdr, which is nil. When we cons anything to nil, it makes a list. So returning the list 4. So we're not returning what we would really want returned here. Well, actually, that's sort of the bad case to show, right? Because that makes the end the list 4, which may not be so bad yet. But when we start looking at here, we're going to get the same thing. We're going to be consing our list structure back up. We're just rebuilding our list structure this way. Okay, so that's the problem with we use cons and tree instead of append and list tree.
On the original one without the yellow.
Yes.
Could you say that we are breaking the tree down into its leaves, making each leaf its individual list, and gluing them all back together? Is that sort of what it's doing?
Sure, it's yeah. You could think of it that way. That each of these leaves is being made into a tree and somehow being appended up into the list structure. Now there may be sub-appends. It's not like we get down to a final step where we have this, right? Because there's some combination of appends on those, and how those combinations apply is based on the tree structure here. But yeah, you could sort of think of it as we're gluing all those little leaves together.
Isn't this something like order n to the 4th? Because we're appending, which, if I remember right, is an n-squared thing, and then we're doing it with this thing twice.
I don't have the code for append in front of me anymore, so let's pull that out. Here it is. So, append, basically what append is doing is it's taking 2 lists, and it's cdring down this first list, okay? And for every single element of this list, it delays, it's basically doing one operation, right? It's doing something with the car. So this is going to be n.
And then we're doing, so it's an end to the 3rd thing that we're doing here then. To do the fringe is
Into the 2nd.
each time we, because we're having to fringe.
Well, so,
the cdr.
well, okay, so we're going through, right, the car and the cdr. But this is actually breaking it up. We're actually only doing this once for every n, right?
We're appending each time
We have a con cell, so n is the con cells, if you think about n as being the number of con cells we have. But if you call the number of con cells the n, then this is going to be theta n squared. So n wouldn't be the number of our fringe elements, because what we're really recursing on is the whole box and pointer structure. So say for the whole box and pointer structure, every single con cell is an n. That's what we're counting for our n's. In that case, then this steps here, ignoring the n, append rather, would be theta n, where n is the count of our con cells. And because we're calling something that's theta n, it becomes n squared. So that's the order of growth in time for this one. Looks like time is up. Any more questions?
Just to continue that order of growth, the order of growth in space, since append is, I think it looks like it's recursive.
Right, append is basically going to be a recursive process on. Actually, no. Did we write? We wrote append. It was recursive. Yep, it was recursive. So that would be. So this is T of n. S of n is going to be also theta n.
For append.
For append.
But it's constant for.
But.
This guy also is going.
This guy is recursive.
Recursive.
I mean, this guy
Doubly
is.
recursive.
Yeah.
It's still so space is n.
Right. So this is T of n, and space is similarly. If we counted on the con cells instead, this is also going to be n squared. Yes.
There's no atom question mark predicate defined, but there is a list question mark predicate in the Greek. So I guess atom is just simply in reverse.
I guess I thought atom was a primitive actually.
It's maybe not in the index by accident.
Actually, John was looking the other day and said they don't have random here either. So I'm not sure if there's a bunch of stuff added on top and it's not in the basic definition of the language.
You don't need list if you really.
Right, you can invert it, but it's odd for them not to provide it.
And what's the order of evaluation for? Not con. Yes. No.
What?
What were we talking about?
We were talking about the order of growth in space and time.
No, before that, we were trying to predict the order that the list would come out in. Like, it wouldn't necessarily be 1, 2, 3, 4.
Well, it is going to come out. So basically here, it's going to pick the leaves off, and it's going to pick the cars off first. So it will actually come out. It's going to do this.
Isn't it going to be working on the cooter, which is just a 4, at the same time as it's working on...
Well, it's appending the fringe, what's resulted from the car, in this case is 1, 2, 3, to the list from the cooter, which would be 4. And then we're going to append the car of this structure, which is going to be 1, to the fringe of the cooter, which here is going to be the list 2, 3. So then we check this. So it is going to preserve the order of the leaves going that way.
But what about the cooter, the 4, that's there at the very top level?
That cooter of the 4, so this is going to be our first recursion level. So we're going to call fringe on the car, and we're going to append the fringe of this list sublist containing 1, 2, 3 to the fringe of this sublist with 4 in it. So our order is preserved.
Wouldn't 4 be first
The 4 waits. The 4 is hanging out there until we figured out, until that stuff can be appended to it.
So append AB, what does that do?
If you say append A, B, assuming that A and B are defined somewhere as lists, is going to take the list that's equivalent to A and the list that's equivalent to B, so the elements of it. So the elements.
I was reading append A to B.
It is appending A to B.
It's appending B to A.
It's appending B to A.
Yeah, okay. A on the front.
So it has a strict
So it's
left right.
pretending A.
Evaluate.
Whatever. I was...
It's sticking A in the front of B.